Please share.
This is now.
Okay, so Marco, you please share your slide.
Okay, I will share it now. So wait a moment. Wait. So firstly, let me thank all the organizers for inviting me to this beautiful conference. In particular, Santosh, my old friend Santosh. Unfortunately, I was unable to come in presence, mostly because of the visa problems that I got during the process. And then now we know that even if I got the visa in time, I would have not been able to come due to these massive flight cancellations that's happening in that part of the world. So in both cases, I would have done the talk online as I'm doing now. So anyway, today I'm going to talk about our recent research, which is related to heavy quarks in the early stage of proton-nucleus collisions. And here you can see a list of my more active collaborators on these topics. So the plan of the talk is following. Firstly, I will give a very user-friendly introduction to the plasma and its evolution. I know that in this conference, you already had very nice lectures from experts in this topic. Therefore, I will limit myself to give just a very short introduction to fix a few key concepts about plasma and its evolution, which are relevant for the second part of the talk, which is, in fact, the heavy quarks in this early stage. After this introduction, I will focus on two quantities that we have been computing in the last few years, which are the modification factor as well as the elliptic flow, in particular for charm quarks. For beauty, the work is ongoing now. And let's see, if time allows, I will also discuss about Quarkonia in the early stage. I'm not sure I will have enough time to do that. Anyway, I put the slides about that. And finally, I will give my conclusions and the outlook. So to begin with, let me start with a very user-friendly, so very informal introduction about the plasma and its evolution. So as you already heard in the, I don't know what's, okay. As you already heard in the conference from the previous speakers in the, sorry, it's out of my control. Okay. As you heard from the previous speakers probably in this conference, we accept the idea that when the energy of the collisions in the nucleus-nucleus or proton-nucleus collision is very large, then the energy density is so large that we can describe the system produced after the collision as an ensemble of very dense overpopulated gluons. And in particular, this overpopulated gluon system is made in such a way that, at least at the leading order in the QC decoupling, it contains color electric as well as color magnetic fields that connect the two colliding projectiles, which can be the two nuclei or one proton and one nucleus, for example. This particular configuration of classical fields develops in the full interaction of two projectiles, and it takes the name of the plasma. So for the plasma, we mean the initial condition for the problem of the evolution of the system in ion collisions. Now, when we talk about this plasma and this physics in general, we introduce one energy scale. This energy scale is called the saturation scale that we denote by QS, or for the purpose of this present talk, we can also identify with, sorry, I don't know what's happening. My screen is completely black.
We able to see your screen?
No, but I'm not. It's completely black. It went black completely. I don't know what's happening.
So you can start it again.
Black. So wait a moment, something is happening. Wait. I really don't know what's happening.
Can you stop Marco, this is Nihar, can you stop sharing and again join?
No, the fact is that even if I push ESC, my screen remains completely black. So it's a problem of my computer, not of the connection.
Okay.
So maybe, I don't know, maybe I should restart my computer completely.
Yeah, take your time, don't worry.
Okay, so I will start my computer and I will reconnect to the session.
Sure.
Okay. Okay, can you see my slides now?
Yes.
Yeah, I'm sorry. I don't know what's happening with my computer. So I will continue from this point. So, yeah, thank you. Yeah, so what I was saying that when we talk about this physical problem, we have this energy scale, which is called the saturation scale, that we denote by QS. So you can think of that basically as the momentum scale or the energy scale, below which the nonlinear effects in QCD become important. So in particular, Gluon recombination become important. And for the purpose of this presentation, to keep things simple, we can identify this QS with this other parameter in the theory, in the model, which is G mu, which basically measures the density of the colored charge in the system. So what we do in this type of calculations is that usually we assume that colored charge, which are the sources of these plasma fields, can fluctuate randomly in the full transverse plane for the two colliding projectiles. And usually these fluctuations are taken to be statistically independent from each other, so from site to site in the transverse plane. When we have a proton, on the other hand, we refine a little bit the model. And in particular, what I will discuss today is based on a model that was introduced a few years ago by Schenke and co-workers, in which they make the assumption that firstly, one identifies for each proton three constituent colored charges that we can identify with the three constituent quarks of the proton, for example. Then these three colored charge, these three constituent colored charges, play the role of the sources of all the small x colored charge that then generate the plasma color fields. So when we take this model for the proton, for the colored charge in the proton, naturally we introduce a saturation scale or a G mu scale, which depends on the coordinate of the transverse plane. Nevertheless, we still assume that fluctuations of the colored charge in the transverse plane are still statistically independent, the one from each other. A refining of the previous models that we introduced recently with my PhD student here in Catania is that also for the nucleus side, when we consider proton-nucleus collisions, we replace a uniform saturation scale on the nucleus with that of fluctuating nucleons. So basically, for each of the proton, or more generally of the nucleon that participates in the reaction on the nucleus side, we introduce three hotspots. So this in general introduces a very anisotropic distribution of the colored charge density in the transverse planes for both the proton and the nucleus. Now, as I said, the plasma works as the initial condition in this problem. Given the initial condition, we have to solve some evolution equation to understand how this initial condition evolves in time. We do that by implementing on a real-time lattice the classical Yang-Mills equations, which basically can be seen as a nonlinear version of Maxwell equations in the vacuum, that here, just for the sake of completeness, I rewrite in the continuum limit using the tau eta coordinates that are quite popular in this framework. So basically, what we do is the following. We assume the plasma as the initial condition, and then we implement using some gauge invariant formulation of evolution of these equations, the evolution of the initial condition. And we studied then several physical observables related to these Grassmann fields. So just to give you a semi-quantitative idea of the type of physics which is involved in this process, I'm showing here the average of the color fields, both for a proton-nucleus collision and for a nucleus-nucleus collisions. So as you can see, from the qualitative point of view, the evolution in the two cases is quite similar. There is certainly a striking difference between the magnitudes of the fields that you produce in proton-nucleus on the one hand and in nucleus-nucleus on the other hand, which is quite natural and expected because in a nucleus-nucleus collisions, there are much more nucleons involved in the collision. So there are many more color charges that produce these initial plasma fields. So that leads to larger intensity of the fields. Nevertheless, the qualitative evolution is quite similar for both cases. In particular, we see that initially the system of fields is made only of longitudinal fields. This is natural. This is just the Grassmann field, which are made of longitudinal fields in the initial time. However, this initial condition is unstable towards the creation of a transverse field. In fact, even though the transverse fields initially are at 0, the time derivative is in general non-zero, as you can see from the Young-Mills equation that I wrote here. Which means that even though initially we have no transverse fields in the leading order Plasma, the Young-Mills dynamics works in such a way it transfers energy from the longitudinal sector of the fields to the transverse sector. And in particular, we form transverse fields on a time scale which can be compared to 1 over QS. That practically means that we form transverse fields on a time scale of the order of 0.1 Fermi, which will be very important to understand heavy quark dynamics later. Another aspect which is quite interesting in these dynamics can be highlighted when we analyze the evolution of the component of the energy momentum tensor. So in particular, when we analyze the energy density of the system and the longitudinal and transverse pressures. So to begin with, let me start with the qualitative picture of the energy density that here is shown by the blue line. And here on the right of the slide, you can see a contour plot, so basically a snapshot of the energy density distribution in the transverse plane at initial time and at some later time when the transverse fields have already formed. So as you can see, from the quantitative point of view, we can measure immediately an average lowering of the intensity of the energy density. This is obviously related to the fact that the system, after the collision, expands along the longitudinal direction mostly. Therefore, since energy is conserved, longitudinal expansion implies that energy density must become smaller and smaller with time. This is not the only interesting point of this, the only interesting point of the dynamics of this system. We can analyze the evolution of the pressures, and in particular, the evolution of the longitudinal pressure that here is shown for a peer collision in the green line here. So as you can see, firstly, we start with a negative longitudinal pressure. Now, negative pressure means simply means that there is an attractive interaction between the two colliding projectiles. This is very similar to the negative longitudinal pressure that we find in classical electrodynamics when we studied the electric field produced by two plates of an ideal capacitor. So no new physics here. Anyway, we see that as time moves on and the system evolves, the longitudinal pressure becomes 0. This means that after some time, the longitudinal expansions happens from the kinematical point of view, but this expansion makes no thermodynamic work. This is just a classical free streaming, similar to the free streaming that we encounter in thermodynamics when we study, for example, the Joule free expansion for perfect gases. Moreover, we see that if we compare the longitudinal over transverse pressure, there is a very strong anisotropy in the system. And this anisotropy remains up to late times, in which this ratio goes to 0. Another interesting aspect is that, as I said, initial energy, the energy density is diluted by the expansion. In particular, we see that after a very short transient time, we enter a dynamical regime in which the energy density follows an evolution equation, which is exactly what we would expect for a perfect gas that makes a longitudinal expansion with 0 pressure, namely free streaming. In this regime, we can already talk about diluted fields, and in fact, it is quite possible that it is in this regime that we can equivalently describe the dynamics either in terms of Gluon fields or also using effective kinetic theories, like the one, for example, produced in the latest year by Kirill, but also by many other people in the community. Now, when we analyze this dynamical evolution, we can also study several other quantities which are important for the phenomenological aspects of this evolution. One of these things is the eccentricities in the coordinate space. So basically, as I said before, when we include these nucleonic fluctuations in these collisions, we can get, in general, an energy distribution like the one which is shown here in the left part of this slide, which is quite anisotropic. So we can analyze the Fourier components of this distribution in the transverse coordinate plane. And we can identify each of these Fourier components with a particular symmetry that would be related to that particular component. So for example, assume that we focus our attention on the eccentricity with n equal to 2, which is called simply the eccentricity. So if the energy density had only epsilon 2 in its distribution, we would have in the transverse plane a distribution like the one shown here in the upper right corner of the slides. This has a symmetry of 2 pi over 2, which means that it is pi symmetric. As you can see, it is an elliptic, okay? It is an ellipse. Okay, sorry, I don't know how to say that in English, but you get the point. If we consider n equal 3, we get a triangular eccentricity. So the symmetry in this case would be of 2 pi over 3. Namely, you can take a point and make a rotation of 2 pi over 3, get exactly the same value of the energy density, and so on. So each eccentricity in this Fourier decomposition identifies the component of this geometrical shape to the total energy density distribution. This is interesting because we can study how this evolves in time. And in fact, we see that, for example, here I'm showing just the first two eccentricity, epsilon 2 and epsilon 3, for 2 cases of proton-nucleus collisions that differ only by the number of participants in the collisions. So you can see there is clearly some quantitative difference between the two, but qualitatively we have the same behavior. So namely, these eccentricities decay with time, which is what we would expect if we had a hydrodynamical expansion of the system. And this type of hydrodynamical expansion can also be studied by analyzing in more details the anisotropies in the energy momentum tensors of these fields. Now, I just showed this very quickly. I will not go into detail about this, just to show that this lowering of the eccentricities results in the increase of the anisotropy in the energy momentum components of these plasma fields, which is something related to elliptic flow that I will mention in a moment. If you are interested in this particular hydro behavior, you can read this very interesting recent paper by Carrington and Mroczynski, in which they studied this hydro behavior in much more detail than the one I'm showing here. One thing that instead I want to focus on is exactly the elliptic flow. Now, I'm sure that in this conference, you already heard a lot about elliptic flow. Now, one of the things that was highlighted in the recent, let's say, 10 or 15 years, but was stressed very much by Schenken and co-workers in 2015, is that in these plasma fields, even though you might not have a hydro behavior of the fields, you still can have an elliptic flow. And this is related to the domain structure of these plasma fields in the transverse plane. Since I will mention this thing in some more detail in the second part of the talk, I here limit myself to show only the qualitative behavior of these things. So basically, we can compute an elliptic flow for the plasma by converting the plasma fields into a gluon distribution function. So we can analyze the moments of this function in the momentum space, extract the second moment, which is exactly the V2, and plot that as a function of the transverse momentum of the gluons. As we can see, we have a finite V2 in this system that, as I said, most likely does not come from hydro behavior, but from the very structure of the domains in these plasma fields. One of the questions that triggered my interest in these things is if, for example, this type of evolution of the plasma fields, and in particular this elliptic flow, can be transferred to hard probes that propagate in these fields, and in particular to heavy quarks. So one of the questions that triggered my interest is, do heavy quarks that propagate in the early stage get some message about these anisotropies from the bulk gluon field? So this opens to the second part of my talk, in which I will discuss the evolution of the heavy quarks in the early stage. So the way we do that is quite classic, I would say. So basically, we implement a relativistic kinetic theory for heavy quarks, which evolve in the bulk evolving plasma fields. So from the practical point of view, what we do is that we implement the Wang equations that are well known in the literature of QCD since the 80s, basically. And again, in the 80s, were made popular by Heinz in his very famous papers about QGP dynamics. And recently, we derived them also in some limit in the same context. So the idea that we implement in our calculation is the following. We have the bulk of the evolving plasma fields that evolve according to the Yang-Mills equations. On the top of this bulk, we implement heavy quarks. So we inject heavy quarks in this bulk, and we study the coordinate, momentum, and color charge evolution of these quarks according to the Wang equations. That basically, if you are familiar with the test particle method in relativistic kinetic theory, for example, are nothing but that a statement of the Boltzmann-Vlasov equation in these external fields. So what we do is that we implement a solution of these equations on top of these evolving plasma fields. So everything from the plasma to the heavy quarks is transmitted by means of the momentum dynamics and color charge dynamics. Now, these dynamics, even without doing any calculations, we already expect to be quite interesting. In fact, here I'm showing a plot of the correlation of the electric and the magnetic fields in the coordinate, this is as a function of the transverse plane coordinate, denoted by R here, measured in units of 1 over QS. And I'm showing both correlation, the correlator of the electric field and of the magnetic color fields of the plasma here. We see that after a short amount of time, there is the a developing in the system of a correlation length, which I denote by psi here, which basically is of the order, roughly speaking, of the order of 1 over QS, where QS is the saturation scale that I introduced in the previous part of my slide. So this means that basically, when we analyze the evolution of the heavy quarks in these plasma fields, the force that they will feel in the fields will be correlated. So the diffusion of these heavy quarks is not like a standard Brownian motion, but it is a diffusion with a memory, okay? This is quite interesting and can be understood also very easily if we look at this picture here. So here in particular, let me focus only on the left side of this plot, in which the orange, roughly speaking, corresponds to a correlation domain. So the so-called flux tube or the flux color filaments that produces in the plasma fields. Instead, the dot corresponds to one heavy quark, and these small segments that you can see here are the trajectories of these heavy quarks, which are computed self-consistently by solving the Wonk equations. So as we can see, if this heavy quarks is quite, how to say, quite massive, so for example, like a beauty quark, or in some limit also a charm quark, it will spend much of its evolution in the early stage within the same core flux tube, which means that the force, which is that this heavy quark feels in this evolution, is time correlated. So the stochastic process of this diffusion is similar to the stochastic diffusion of a heavy particle in a medium with memory. Just a moment, sorry, I need to drink some coffee. Sorry. So another thing that we analyzed, that we realized, is that we can compare the evolution time, which is typical of the lifetime of this early stage, which is a small fraction of Fermi over C. Remember, this is just the early stage of the collision, with a sort of, let me call this a thermalization time, even though it should be called the equilibration time, namely the time which is needed to the heavy quarks to get at equilibrium with the plasma fields. We estimated this equilibration time in some previous work, and we found that it is quite larger than the typical lifetime of this early stage. Now, this means two things. Firstly, it means that since equilibration time basically is too large in this short evolution, the evolution itself will be dominated by diffusion. In a language that is more common to the people in the community, we could say that the drag effects would set up at a much later time, when the early stage, the evolving plasma already formed the QGP. And the thing is that this evolution time is in line with the memory time of the fields. Therefore, we expect that memory will play some effect, which practically will lead to nonlinear evolution of several quantities, for example, the momentum diffusion. I will show that in a moment, just very quickly. Let me show you here just a kind of unfairly short review of some of the work that other people have done. As you can see, these type of topics started to attract some interest in the recent 5 years, maybe, from several groups in the community. And most of them focused on the momentum diffusion, which has been studied within several theoretical frameworks, both for the quarks and very interesting also for the jets. So this is something that is getting some type of interest. And in particular, what all the calculations agree on is that momentum diffusion, either if you look at heavy quarks with soft momentum or if you look at jets, is quite substantial, even though the early stage is short-lived, which is quite interesting. Very quickly, let me show one of our results on this. In particular, let's focus only on the right side of the slide, in which I'm showing the momentum diffusion of the heavy quarks in some nucleus-nucleus collision that we obtain for several values of the saturation scale. We clearly see that there is early time evolution in which the evolution of this quantity is nonlinear. This is directly an effect of the memory that is produced in the plasma fields. Then at later times, we find an almost linear evolution of this momentum diffusion, which means that we enter the regime which is very similar to the standard Brownian motion without a drag coefficient, because as I said, the drag becomes important at much later times. Now, one interesting aspect of these things is that what I discussed so far, and what also other people in the community discussed so far, focused only on the leading plasma solution. So basically, it is a solution of the Young-Mills equation for the early state, for the initial time, in the limit in which the QC decoupling goes to 0. In this limit, we get that very nice picture of longitudinal fields that connect the two colliding nuclei. However, when we try to introduce finite coupling corrections to this picture, then we generate some other types of fields. The two major effects of that is that, firstly, we break the longitudinal boost invariance. So the fields will be dependent on space-time rapidity eta. Secondly, due to this space-time dependence, and also from the Gauss law, basically, we will get also transverse fields already in the initial stage. Now, of course, we are not able to compute exactly the spectrum of these fluctuations with finite coupling, although there are in the literature very nice calculations done in the small coupling limit, for example, by François Gély and his co-worker Thomas. In our framework, what we do is that we basically drive the size of these fluctuations by just one parameter, which is denoted by this capital delta here. And this framework is basically borrowed by a previous study by Kenji and François Gély. You can think in some sense that increasing delta, capital delta here, amounts to increase the coupling, the QC decoupling in this framework, which amounts to increase the strength of these fluctuations. As we can see, if we increase delta, so if we enlarge the contribution of the fluctuations in the system, we get some sizable effect on the bulk. For example, here I'm showing the ratio of longitudinal over transverse pressure. We see that for sizable value of delta, we get that this ratio is very different from the one that we get without fluctuations, which in fact is in agreement, you see the black line, with what I showed in the previous part of my talk. This basically means that when we introduce these fluctuations in the calculations, we are drastically modifying the bulk, the gluon bulk. So we can say, roughly speaking, that fluctuations actually are in our bulk. However, very surprisingly, what we found is that when we compute within the same framework the momentum diffusion of the heavy quarks in the fields with fluctuations, these fluctuations give almost no contribution. Now, there is a caveat here, namely that the calculation that I'm showing here was computed only in the very large quark mass limit. So to be completely fair, this is not a calculation obtained, let's say, for the charm quark. Okay, it is most likely a calculation that works very well for a B quark. Okay, nevertheless, it is quite interesting because although we have fluctuations, we find almost no effect of them on momentum diffusion. So basically, on the diffusion coefficients of these heavy quarks, as long as we limit ourselves to the very large mass limit. At the moment, in the literature, at least to my knowledge, there is no calculation of this kind done with physical quark mass, heavy quark mass. Our understanding of this is that if we take the very large mass limit, then we can relate very easily the momentum diffusion, so basically the diffusion coefficients of these heavy quarks, to, as you can see here from these equations here, to the 2 times correlator of the color electric field of the Plasma fields, or the evolving Plasma fields. So our guess is that even though we introduce fluctuations, then in the short lifetime of the early stage, these fluctuations are not strong enough to break the time correlations of the Plasma fields. And this results in almost unchanged diffusion coefficients of the heavy quarks, as long as the large mass limit is considered. We are now running calculations for the physical quark mass. So I don't know what will happen, but so far this is the situation of our results. We can go even further and compare some of our theoretical predictions to phenomenological quantities, namely to quantities that can actually measure in experiments. So here I'm showing one of these results, which is basically the nuclear modification factor that I computed with Santosh in 2018, so 8 years ago, mostly 8 years ago. And we were the first ones to compute this quantity in the literature. I mean, when we in the context of coupling the heavy quarks to the Plasma fields. Now, here we also decided to compare our prediction with some experimental data. Now, clearly, to be completely fair, I have to say that even though our theoretical calculation in this particular setup was quite close to experimental data, and nowadays we take that just as a kind of, let's say, fortunate accident, because our first theoretical calculation contained a lot of assumptions and simplifications. The most important were that we were doing calculation only in a static box. So there was not a longitudinal expansions. And moreover, we were considering only 2 color calculations. Nowadays, we've done calculation also for 3 colors, as I will show in a moment. Nevertheless, what we found quite interesting already in 2018 was that despite we cannot be very quantitative on this quantity, we already were able to reproduce the qualitative shape that was observed in experiments, which was kind of softly suggesting that this type of interaction of the heavy quarks with the Plasma fields by itself could be already able to explain at least part of this tilt that you observe in the modification factor in the proton nucleus collision, which is quite different from what we've observed, for example, in the nucleus-nucleus collisions. More recently, we computed this modification factor again for period collisions, but for much more refined system. So we have 3 colors, we have longitudinal expansions, we have fluctuating nucleons in the nucleus size. So this is quite a more realistic calculation. And as expected, in comparison to previous calculations, we find some kind of lower effect on the modification factor. So as we were already guessing in 2018, it is likely that the plasma, the heavy quarks evolution in the plasma, in the evolving plasma, might be able to explain part of this tilt in the spectrum of the heavy quarks, but it could not be enough by itself to explain the full modification factor, which is measured in experiments. Okay? but we already knew that, so no surprise here. However, very recently, we also computed the elliptic flow of the charm quarks in particular, which we did not compute with in the first works we have done with Santosh. Now, as I said, when we consider the bulk plasma fields, we expect that even though we do not have a very hydro-like expansion in the transverse plane, we expect some elliptic flow. In fact, if you remember, I showed before a qualitative plot of the elliptic flow in the plasma fields, and I will show that again now. So if you don't remember that, do not be sad. I will show that again in a moment, and I will explain that in much more detail. I anticipated in that part of the talk that we expect some V2 in the plasma just because of the structure of the plasma fields in the transverse plane. And here, with my student Gabriele, we prepared this very nice plot, which qualitatively explains why we expect anisotropy, even though we do not have a real flow in the coordinate space. So the idea is the following. As I said, you can think of the distribution of the plasma fields in the transverse plane as a distribution which is distributed in many correlation domains. So, for example, you can focus your attention on one of the hotspots that can be produced in a proton-nucleus collision, like here, and make a zoom on that hotspot and analyze the domains around some point. So let's say, for example, around the central point of this pink domain here. So around that point, we can build a full correlation domain. Then that domain will be surrounded by other correlation domains. Now, the fact that we have correlation domains means that, for example, if in this point, in the midpoint, the color electric fields points for that particular time and in that particular event along the direction which is given by the arrow here, then nearby, because of correlation, we still have color electric fields that will fluctuate exactly in the same direction. Which means that within one single correlation domain, we can, roughly speaking, identify a preferred direction for the color fields. Then we can repeat these arguments for the other correlation domains that surround the one we are focusing on. So what happens is very simple. If the energy density was distributed uniformly in the full interaction region, like for example it happens in a nucleus-nucleus collision, then averaging over the full transverse plane would lead to a complete randomization of this direction of electric fields. So basically, on average, event by event, we would find no anisotropy, roughly speaking. However, in the case in which we have focused hotspots in the transverse plane, as in PA, for example, as it is shown here, it is quite possible that averaging over the full transverse plane does not wash out completely this domain-like structure of the plasma fields, which means that this domain-like structure, this kind of average anisotropy, will be present event by event in the fields. Therefore, we will expect some type of anisotropy initially, even though we do not have the hydro behavior. As one of my friends was saying at some conference a few years ago, we have flow without flow, which in fact it is exactly what's happening here. We do not have hydrodynamic flow, most likely, or possibly, I don't know that, but we still have an elliptic flow because of this intrinsic anisotropy in the momentum space. Now, the way we do that, we build
So Marco, you have 5 minutes left.
quantitatively. Only 5? Okay, so I will skip technical details, okay? So basically, as I said, we find an elliptic flow for the plasma, which is shown here. This is basically the same plot that I shown in the first part of the talk, which just comes from the domain structure of the plasma fields. And we found very recently that this V2 is transmitted also to heavy quarks, in particular to charm quarks, as it is shown here. This is computed at 0.4 Fermi over C in proper time, that we take as an average measure of the switch time between the plasma stage, the evolving plasma stage, and the QGP stage. We compared, in particular in this result, the calculation coming from different setups, and an elliptic flow computed from event plane method and also two particle correlator methods, to be sure that firstly we get the same result, and secondly that the VT obtained is not numerical artifact, but it is actually something that is intrinsic in this type of dynamics. Then we try to make even more striking prediction. So basically, we took our result for the charm quark elliptic flow, and we adopted the simplest naive hadronization mechanism by equiescence. With that, we computed the V2 that we would obtain for J Mason from this type of calculation. And we compared that with some data obtained by CMS, how it's called, the collaboration. So what we found is that, of course, with the caveat of assuming a very naive hadronization mechanism, that most of the V2 that is measured in CMS could be explained already by a V2 which is formed in the early stage. Okay? So since I have left only a few minutes, I will skip this Quarkonium, and I will directly jump to my conclusions. So in particular, what I discussed in this talk is that we have adopted the evolving plasma picture to study the early stage of PA and AA collisions. And we have coupled this evolution to the collision to the heavy quarks, so charm and beauty, in this early stage. And we tried, within some type of simplified model, to compute some effect that this evolution would have on physical observables, in particular the modification factor and elliptic flow. And we found that, in particular, the elliptic flow is quite affected by the bulk anisotropy of the plasma fields. Just to give you a very short outlook of what we are studying right now. So in particular, what we are doing now, in collaboration with my PhD student and with Paul Gossiot and George Jacqueline, we have implemented a quantum kinetic evolution of these color charts for the quarkonium, using a formalism very similar to open quantum system formalism, to study in particular the melting of how this evolution in the plasma stage affects the melting of the Quarkonia, which is something that they already started to study with a semi-classical approach with the Santosh and also with Gabriele in Catania. And what we are also doing now is making a merge of this early stage evolution with relativistic transport to study QGP, so that we can make a full evolution from the very early stage up to the hadronization stage for what concerns the heavy quarks. So Santosh, for me, it is enough. I finished.
Thank you very much. So any question? Any question? Okay.
Hi, I'm Jean-Paul Blaiseau.
Oh, hi, Jean-Paul. Yes.
Hi, Marco. You mentioned at some point that you were taking care of the distribution of quarks in nucleon in your
Yes, that's correct.
estimate of the initial energy density. My question is the following. Does this have any effect on the V2 that you calculate, or this
yes, Jean-Paul, yes,
average out?
Absolutely, yeah, absolutely, yes. We can see this, for example, in this plot. I hope you can see my white slide, the integrated elliptic flow here. This is one of the things that you can measure directly to see how changing that distribution affects the V2. So firstly, what we can see is that if you change the number of hotspots that you put in the calculations, change the initial eccentricity, and change also the initial distribution in momentum space. In fact, if you integrate the elliptic flow, as you can see here, the left side of this slide, I'm plotting the integrated V2 as a function of the number. Here I call that the number of participants. Basically, you can see that as the number of hotspots that you put in the calculations, but not so. There is clearly a dependence of that on the V2. But not only that, you can by hand tune a little bit the distribution. So change, for example, the size of the Gaussian that you use to distribute the colored charge that diffuse on top of this constituent colored charge. Or, for example, you can do that by gene work, like Björk Schenk did in previous works. And that definitely affects the V2.
Yeah, hi Marco, this is Sören Schlichting here. Hi.
Hey, hi.
So I mean, I also have a related question on this V2.
Yes.
Right? I mean, I mean, in principle, if you take this gluon V2, which you have here, right? I mean, this has the wrong
Yes.
systematics in comparison to experiment, right? That it goes down with increasing
definitely, yes.
multiplicity,
Yes.
and it's also, I mean, it's also very short range in momentum. Now,
Yes.
what I didn't understand is when you compute the charm V2.
Yes.
Then, I mean, you correlate the charm with some soft hadron somehow, right? I mean, that's how the V2 is calculated.
Absolutely, yes,
essentially,
yes.
right? So
That's correct, yes.
So what I don't understand then, because this part of the V2 that the gluons carry is not actually the soft V2 one measures at the end, right? Because it has sort of the wrong systematics, right? So
Okay.
So
Yes.
how does that affect then your measurement of the charm V2 and your
Yeah,
claim that,
that's-
that
yeah,
most
you're-
of it is built up early? So this I don't.
Yeah,
fully
yeah, that's,
understand.
you are. So, of course, you are right on that. However, let me show you here the differential elliptic flow that you find in the Glasma calculation. So, we found that the peaks of this Glasma V2 develops around, let's say, between 1 and 2 GV, which is exactly what you would expect, because you have only one scale in this problem, which is the saturation scale, which is in this problem around 1 to GV on average. So our interpretation of that is that you are basically transferring more anisotropy to the heavy quarks exactly in this kinematic range between 1 and 3 GV, let's say, which in fact is the largest contribution that we find for the V2 of the heavy quarks here, as you can see. So, so basically that's it.
Okay, thank you. So let's then thanks Marco once again.
Yeah, it was my pleasure. I'm very sorry, Santosh, that I was unable to come in presence. I'm sure it would be very stimulating to be there now.
No, it's fine. We
But-
can understand. We hope
Yeah.
next time you will pay a visit to
Yeah,
us.
hopefully. Also, I'm sad that we could not arrange my birthday party.
Oh,
That
yes,
would be-
yes.
would have been-
We work you will do here probably,
Yeah.
yeah, but we could not. Okay.
Yes. Okay, next time.
Okay,
Okay,
next
so
time.
thank you. So see you soon.
Okay, thank you. See you.
See you. Bye-bye.
Okay, bye.